Hello everyone, I am Shine and you are watching Civil Engineering Tips channel. We're going to start a new playlist of Shear Wall Design in ETABS. And this is the first tutorial of that playlist. Here we will discuss everything about shear wall. If you have problems and complexities about designing a shear wall, then you can go through the whole playlist, each video tutorial one by one, and you will be able to design a shear wall very easily. And for that, to design a shear wall, we will use a software, and that is ETABS. So without further ado, let's dive into the first tutorial of this playlist. Let's first discuss about the definition of shear wall. Both column and shear wall is going to resist the lateral forces coming to the building. If a RCC wall is subjected to the lateral forces, then we call it as a shear wall. But if a shear wall is not subjected to lateral force, or that wall is not designed for lateral force, then that wall is not called shear wall. So to confirm a wall as a shear wall, you have to induce lateral force on that. Next, we will discuss why do we use shear walls. Generally, non-load bearing walls are noticeable in the RCC buildings. We use these walls only for privacy and weather issues. Obviously, these are non-load bearing walls. The effects of wind forces increase in significance as the structure increases in height. BNBC, which is the building code of our country, imposes limits on horizontal movement or sway. Shear walls are generally used in high-rise buildings that are subjected to lateral wind and seismic forces. In some cases, shear walls also carries gravity loads. Both shear wall and column are responsible to resist the lateral forces, but there are a lot of differences between them. We have to know what are the differences between shear wall and column. Let's discuss about shear wall first. A vertical element designed to resist axial load, lateral load, or both with a horizontal length to thickness ratio greater than 3 used to enclose or separate spaces. So if the L by B ratio is greater than 3, then we are going to call that vertical member as shear wall. But if L by B ratio is less than 3, then that has to be designed as column. This difference is based on the physical and appearance of those two vertical members. These are not any technical difference. Next, we will discuss about the technical difference between shear wall and column. Difference between shear wall and column on the basis of moment distribution or bending moment. In first figure, we're observing the bending moment diagram of columns and beam as well, and these bending moment diagrams are taken from ETABS software. But the figure on the right side presents the bending moment diagram of shear wall only. If we observe the bending moment, then we will know that the bending moment at the base is maximum for shear wall, but for column, bending moment diagram is little bit different. In this figure, we can observe the bending moments of shear wall and column more clearly because there is no bending moment for beams. Here we can see that the bending moment diagram of column is like this, and the bending moment diagram of shear wall is like this. So what is the conclusion and what is the result? In case of column, the point of contour flexure is 0 in the middle of the story. Here we can see that the point of contour flexure, it is 0 in the middle. The maximum bending moment will be in the top or in the bottom for column. So formation of plastic hinges or yielding will be at the top or bottom of the column. But in case of shear wall, the maximum bending moment will be at the bottom of the story. That's why the plastic hinges or yielding will occur at the bottom of the shear wall. We should design a shear wall in such a way that the yielding should be at the base. If the shear wall is not designed properly, then the yielding will occur at the higher level. So we will ensure through capacity design that the yielding is at the base only. The difference between column and shear wall cannot be made based on ratio of thickness and length. Any thickness to length ratio, we cannot declare it as shear wall. The difference comes from the bending moment diagram. So if we design a member that has bending and yielding at the base, we can treat that as a shear wall. Otherwise, if there is a possibility of hinges at the top and bottom, then it has to be treated as column. Shear wall only yields at the base and it only yields in flexure, not in shear. Now let's discuss about a very important question: what if we increase section sizes of column rather than using shear walls? It will cover the maximum building area and the building cost will be increased. Behavior of shear wall is influenced by the shape of the wall and their plan position. So increasing the size of columns is not acceptable because it will not be economical for the clients. The figure given below is showing the various shape of shear walls. You can use these shear wall shapes in your buildings, whichever is feasible to construct. Now let's classify the shear wall. We can classify the shear wall with the help of the ratio of the height of the shear wall and the length of the shear wall. If the ratio of height of the shear wall to the length of the shear wall is less than 1, then we call it short shear wall, and the failure in this type of shear wall occurs as shear failure. And if the H by L ratio is in between 1 and 3, then we call the shear wall as squared shear wall, and the failure type is shear plus flexure. If the height to length ratio is greater than 3, then we call it cantilever shear wall, and we observe here flexure failure. Now we will discuss about the usefulness of using shear wall. In the figure we can see that there are shear wall provided on the right side and left side both, and this type of shear wall resists bending in one plane, and here we get good torsional stiffness. The next pattern of shear wall is on kind of L-shaped shear wall, and this type of shear wall resists bending in both planes, good torsional stiffness, and here we get good torsional stiffness also. This type of shear wall are not called shear wall, these are called core walls, which are used for lifts, and core resists bending in both planes, and here we get poor torsional behavior due to the eccentricity. If we can manage the eccentricity by shifting this core wall inside the building, then it can provide us good torsional stiffness. As example, this type of shear wall are symmetrical, and here we can get good torsional stiffness. Here we can see that this building is very narrow, and we can separate this building in two parts, and we can provide the core shear wall like this, and here the core resists bending on each section of the building independently. Relative shear displacement in movement joint. So this is all for today. We will discuss more about shear wall in the next tutorials. We will cover everything about shear wall design and the detailing. Till then, stay happy, stay safe. See you in the next tutorial.